All right, let's talk about this idea of a multi-section transformer. So we just did a little bit of discussion on this notion of a theory of small reflections, which you can think of it as a simple analysis of the special case where n equals 1. Right? So now we're going to extend it out to just n, capital N, possible connections of these little transformers, and then ask ourselves what happens when we calculate the reflection coefficient looking down this entire little array here. Okay, so imagine some reflection here, a net reflection coefficient gamma. And we again have all of these little partial reflection coefficients here. Okay, so I might draw these out like that. So these are little reflections and so on. So this would be gamma sub 0, gamma 1, gamma 2, dot, 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 gamma sub n minus, that's n minus 2, excuse me. Gamma sub n minus 2, and then you get a gamma sub n minus 1, which would be here. And then finally over here, there is a gamma sub n corresponding to the partial reflection at the load. Okay, so 0, 1, 2, and so on. So generally speaking, I would write gamma sub n, the nth one, 1, 2, 3, 4, n, pick one at random, would be calculated as follows. Z sub n plus 1 minus z sub n divided by z sub n plus 1 plus z sub n. So that's the nth partial reflection coefficient. Okay, so how do I calculate this net gamma here? Well, first things first, we're going to assume the length of all of these lines is identical. Okay, so we gave it that theta here, which you remember corresponded to some beta L at a given frequency, right? And so each of these lines has the same length. So what can we do with that? So let's start by just saying, okay, I have this reflection coefficient here, gamma. Remember, the theory of small reflection said it was equivalent to, or was approximately, the sum of this first reflection here plus the reflection with that phase factor at the load down here. So I'm going to write a little bit here. Assume all of this stuff over here is getting squished into some equivalent load impedance, Z sub L prime 1 or something like that. Okay, so I'm just going to call that ZEQ1 maybe. But the idea is I need a gamma here. So I'm going to call this a gamma 1 prime. So it's not the partial reflection coefficient. It's if I took all of this and lumped it together into a load, what would I see here? I would have a single transformer. So it would follow the equation, which we just derived in the previous section. Gamma is equal to gamma naught plus, I'm going to call this gamma 1 prime e to the minus 2j theta. That is the reflection coefficient for the small reflections, right? At least approximately, we can write it as that. But this gamma 1 prime follows a similar rule because I don't really know what this is. Everything's been lumped together. So what if we then repeat the process by saying, okay, there's some equivalent lump over here. So I'm going to call that maybe gamma 2 prime or something. We'll even draw it in red just to emphasize it's not the partial, it's the equivalent load. And if it helps, you could call it maybe Z or gamma EQ1 if that helps. That's also a good way to keep them straight. But the point is this guy here is going to follow its own expression, which is going to be gamma 1 plus gamma EQ2, or you could call it gamma 2 prime or something, give it a name, e to the minus 2j theta, like that. So that's this reflection coefficient seen looking into this equivalent load. But then the same logic applies to this guy here, which will be gamma 2 plus, gamma 3 prime, or gamma EQ if you want, e to the minus. And you just, it's a recursive equation that repeats all the way down to the end. So what you'll get is something like the following. Gamma is equal to gamma 0 plus gamma 1 e to the minus 2j theta plus gamma 2 e to the minus 4j theta plus gamma 3 e to the minus 6j theta plus all the way out. We keep going out. There could be 500 million of these things. When you eventually get to gamma sub n e to the minus 2j n theta. Okay, so this nice nice finite summation out to the nth term here. So that's pretty straightforward. It gives us a nice recursive relation. And remember, the idea is these are all small reflections here. So each of these little discontinuities is relatively minor. So this is not an exact equation. It's better to remember this is an approximation. But it has nice desirable properties, as we shall find if we start imposing some interesting conditions. So let's go ahead and do that right now. Okay, so I've rewritten this gamma here real quick so that we can do some fancy manipulations here. So what I'm going to do, you see I've just written out this term a little more explicitly. I'm going to lump terms together by the first and the last. So this 0 and this n, I'm going to bring them together. This term here and this one, I'm going to lump them together. And then so on going down the line. So what I will get is something that looks like this. Gamma naught plus gamma sub n e to the minus 2j n theta. So I'm just rearranging terms here. I'm going to block them in parentheses too, just so it's a little more explicit. I'm going to get a gamma 1 e to the minus 2j theta plus gamma sub n minus 1. I'm going to play with the exponent a little bit. E to the minus 2j n theta times e to the 2j theta. Like so. And then we'll do it again for 2 and n minus 2. So I will get something like gamma sub 2 e to the minus 4j theta plus gamma sub n minus 2 e to the minus 2j n theta e to the plus 4j theta. So still rearranging terms a bit. And this will go on all the way until I reach gamma sub n over 2. And the exponent that goes with this, the phase term, will be in e to the minus j n theta. So 2 times n over 2 will evaluate out. Okay, and there's no other term for this one to balance out. This is for the, by the way, this is for the special case of an even n. You can do the same sort of analysis for an odd. You just have to rearrange a couple of terms accordingly when they meet in the middle here. So just make a note. I'm assuming an even number for n here. This last term here kind of changes if it's an odd number. So what I'm going to do now, a fun little trick with this matching network is I'm going to assume these reflection coefficients are all balanced. So I can finely tune that, remember? I have control over what each of these reflection coefficients are by simply picking the appropriate impedances for these lines and making them satisfy this equation. So I'm going to pose a symmetry condition whereby this gamma naught equals gamma n, gamma 1 equals gamma n minus 1, 2, and so on. So that we'll call that symmetry. All right, so it doesn't mean the impedances are the same. I am carefully choosing the impedances such that the reflection coefficients are the same. So again, don't confuse the impedances with the reflection coefficients. I am choosing impedances to give matching reflection coefficients, or at least partial reflection coefficients. So when that happens, we can do a little bit of a simplification. So again, gamma is equal to this guy here. I'm going to get a gamma sub 0. And then I will get basically 1 plus e to the minus 2j n theta, right? So now I can factor out again, plus gamma 1, and then I'll get an e to the minus 2j theta plus e to the minus 2j n theta, with an e to the 2j theta. So I'm just kind of factoring these guys out. Plus dot, 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 all the way out to the end. Now I'm going to do one last fun little trick. I'm going to factor out this term here, e to the minus j n theta. So what you'll get is e to the minus j n theta. And something interesting happens when I make this little factorization. I get a gamma sub 0 times e to the plus j n theta plus e to the minus j n theta. Isn't that interesting, right? Because remember, that's going to be a cosine there. And the same thing will happen with this term. I'll get a gamma sub 1, and I will get e to the, so this is the part where it's a little tricky, so let's make sure we don't make a mistake. I'll get a plus j n minus 2 theta plus e to the minus j n minus 2 theta. So if you work out the exponents there, you can see that symmetry. And then we go plus dot 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 all the way out to the end, and this term is factored out, so I just get a gamma sub n over 2. So that is interesting because remember, this will be cosine of n theta. This term here will be a cosine of, let's see, parentheses within a parentheses, n minus 2 theta. And you notice the pattern is now emerging all the way out to forever. And sorry, there's actually a 2 in front of all these guys as well. So I'm now going to factor out the 2 to the front here. And what you basically get is gamma is equal to 2 times e to the minus j n theta. And we'll get this sort of expression here. We'll get a gamma sub 0 times cosine of n theta plus gamma 1 cosine of n minus 2 theta. And then I'll get an n minus 4, n minus 6, n minus 8, so on, dot, 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 plus 1/2 gamma sub n over 2, because I factored out the 2 over here, and then we close the bracket. So now I'm going to rewrite this just a tiny smidge more, and we get basically the following. 2 e to the minus j n theta times the summation from n equals 0 to n over 2, and I get gamma sub n cosine of the quantity n minus 2n theta. Okay, so that is our magic expression, our magical result. So this is for the even case. If I do odd n, you get a slightly different result, but that's okay. So this is a Fourier series, isn't it? Which is very interesting. A Fourier series. And in particular, this is going to be this gamma here. So I'm going to write this as gamma of theta. Okay, so it's a Fourier series about this electrical length theta. So that is the interesting property of these small reflections added up to a bunch of multi-section transmission lines, where in effect, I can shape my reflection coefficient by carefully choosing the length of my line and my my gamma here. I carefully tune these gamma coefficients by following this expression here again. So I can carefully choose my impedances to create these gammas, and they become the Fourier coefficients, which mean I have a lot of control over the shape of my frequency response. So that is where the power of this kind of multi-section matching. And the more terms I add, the better this approximation will become. So you can get surprisingly good results with 2, 4, 6, 8 matching networks. You don't need 50 to 100 to get surprisingly decent results. Okay, so that is the power of the theory of small reflections coupled with lots and lots of the multi-section, multi-section transformer, okay? So it's that whole notion of a Fourier series is coming back, and will have very interesting properties, which we'll explore next time.